Hello everyone. In today's session, we will be discussing about different variants of load store instructions, which belongs to different addressing mode. One thing that we need to know is when it comes to LDRH, STRH, LDR-SP and LDR-SH instructions, there are some conditions. You cannot use an offset which is greater than 8 bits, that is condition number 1. And condition number 2 is you can't use scaled register offset in any of these cases. Okay, if you try to run these instructions, you will get error as shown here. See, you will get errors. Okay, any of this is not allowed. Okay, so that clears all our errors. So now let's just focus back here. Okay, so you can see two labels here, initial and value 1. Let's see what are those. As you can see here, initial is a label which is defined within read only area. Okay, and that means we can only load data from here. There are 4 32-bit values as shown here, okay, which can be loaded. Then we have value 1, which is a label in read write area. From this particular section you can load data and you can even store the data. Okay, so now let's see what is happening here. The very first instruction we see is LDR R1 comma equal to initial, which means whatever address is marked by the label initial, load it to R1. Let's do that now. Okay, and after executing the first instruction, we know 48 is the memory location pointed by the label initial. Let's access that memory location. Okay, so as you can see here, these 4 values are stored in this particular memory location. Okay, let me open one more memory window. Okay, so that we can see what is happening in both the memory locations, and let's check what is happening in this particular memory location. Okay, so because our next instruction here is LDR R6 comma equal to value 1. Let's get the address of value 1. It is 4 and all zeros. Okay, so its initial value is 0, while here already some data is stored. Okay, let's see what's happening next. This, as we mentioned here, is register indirect addressing mode, because we have an instruction here LDR R0 comma content of R1, okay, wherein this is exactly same as this particular instruction, that is pre-indexed with immediate offset, such that we have considered a value 0 as an offset. So what we know about register indirect? Offset is 0, so effective address or the location from which data should be loaded is R1 only. Okay, so what is R1? R1 is the location initial. So as we already know, in the location initial, this particular values are stored. So what should happen when this particular instruction is executed? LDR loads 32-bit data from the memory location and stores it in R0. So it means the very first 32-bit data, A, B, C, D, 1, 2, FF should be placed in register R0. Let's see that happening. Yes, and why is it stored in this way instead of FF 1, 2, C, D, A, B? Why is it stored like this? Because our system here follows Little Indian concept. First instruction is executed. What is the next instruction that we notice here? This is an example for pre-index with immediate offset. Why is that the case? Because we have used a constant value. Offset is what exact value you will be adding or subtracting with respect to base register. R1 here is base register. Okay, so let's see what's happening here. We have to add R1 base register content. What is R1 content? 48 with 4. So what will be the answer? So what is the address you will get? 4C. Okay, because 12 in hexadecimal is nothing but C. And then from that particular memory location, you want to access the data and copy it to ARM7. What does that mean? Here what will be the 4C? Okay, so this particular value 77665544 should be copied and pasted to the register R7. Let's see that happening. Okay, so we got this value in this particular location. Okay, next we want to store a value 8 in register R5. Okay, because in the next case we are using pre-index with register offset. It means instead of a constant to the base register, we want to add register content itself. What is R6 content? R6 content is 4 and all zeros. Okay, now to this particular R6 content, we want to add R5 content. And what is R5 content? 8. So what is the value? 4 all zeros and 8. Okay, so from the location, now this is the location. Do we want to load something? No. We want to store the content of R7. What is R7? R7 is 44556677. This data we want it to be copied in this particular location. So you are using store. Let's see that happening. First we have to execute this instruction where R5 is loaded with the value 8. And now our required data is stored here. Okay, so here what we have is we are loading a value 1 to register R3 because we want to take scaled register offset, which means take a register, okay, and shift it or rotate it by certain value. That content is to be added with this particular base register. Okay, so what it means is now 1, when you perform LSL #2, what internally happens is 1 into 4, 4. So 4 is the value added to R1. What is R1 content? When you check here, R1 is 48. Okay, so that is nothing but 4C that we checked that time. So from the location 4C, it's saying load only 8 bits of data because it's LDR B. Okay, and then copy it to register R8. Let's see that happening. First of all, let's check the location. Okay, from this location 4C, they want to copy only 8 bits of data, means 77 should be copied to R8. Let's see that happening. Okay, first we are executing this instruction and loading R3 as 1. Yes, now R8 gets the value of 77. So the very next instruction is we want to load half word, that is 16-bit data, okay, from address in R1, that is 48 plus 4. What is 48 plus 4? Just now we calculated it was 4C. From this location, last time we loaded 8-bit data. Now we want 16-bit, means 6677 should be loaded in the register R2. That is the first thing we notice. And what do we notice? There is an exclamation mark. This mark, if you notice, it means it belongs to writeback category, and whichever instruction belongs to writeback category makes one thing sure, that is they update R1 with the same address as the effective address. So what is effective address in this particular case? Effective address is actually R1 plus 4. R1 is 48 as we notice here, plus 4 is nothing but our 4C, but this value is updated as R1 also. Okay, in the both place, you know, it gets updated. Effective address is also updated and R1 is also updated in case there is an exclamation mark. So now what should happen is this value, that is 6677, because only 16-bit data should be loaded and placed in the register R2, okay, here. Okay, along with that R1 also should be updated with the address 4C. Let's see that happening. Okay, now we want to store half word or 16-bit data in memory location at R6 added with contents of R5. Okay, and what category this belongs to? Pre-index write back with register offset. Why is it register offset? Because contents of that is actually added to R6. Okay, so let's see what exactly happens here. Okay, so before that, now what is R6 content? If you notice, R6 is 4 and this is your R6, and at the same time, what is R5? If you check here, R5 is 8. So like last time, here the effective address that we get is nothing but 4 all zeros and 8. Okay, let's see that here. Okay, 4 all zeros and 8. This is the value we are speaking about. But what we want to do is nothing but we are not loading the data. We want to store the content. And which content are we speaking about? R0. What is R0? This value A, B, C, D, 1 to FF. Out of this particular value, only 16 bits, which will be the 16 bits considered 1 to FF. This particular section or this particular value, okay, should be now copied and placed in the address specified here. But one thing we notice is exclamatory mark. What it means is this is the new value of R6. Let's see that happening. FF12. R6 is now 4 and all zeros and 8 as expected. Okay. Next we are considering the case of pre-index write back with scaled register offset. So what should happen in this particular case? First of all, exclamatory mark should be there to ensure it belongs to write back category. And what do you mean by scaled register offset? The content getting added to the register should be some register which is shifted or rotated by certain value. Here they are saying R3 should be shifted left by 2 times, which clearly means R3 content should be multiplied by 4. Why it should be multiplied by 4? To know that, you can check about shift operations. Now let's just focus back here. So what is R3? R3 is still 1. So 1 into 4 is nothing but 4 only. This should be added with the content of R1. What is our R1 content? It is 4C. Okay, so what do you think is the value you'll get here? 5 0. Okay, all hexadecimal calculations are going on. Okay, so this value is your effective address as you expect. Along with that, it should be updated in R1. Location 50, whatever data is there, copy to R0. What is initial R0 value? This one. Now this will get updated along with the updation of R1. Okay, let's see that happening. So before that, let me just write 50 here. So this is the location that we have to discuss here, because that's the effective address. From this particular location, because it is LDR, 32-bit data had to be copied. Okay, and then here what they are saying is, along with loading this content to R0, which has happened, we even had to update the R1 content. As expected, 50 is the value getting updated. For any instruction, LDRH or STRH, LDR or STR, what you should notice, the address getting computed by any of this approach should always be divisible by 2. That is even addresses for LDRH, STRH, and divisible by 4 for LDR and STR instructions. If this particular condition is not met, in that particular case, you will get memory alignment faults. We have something like move R1 comma has 0x4 and all zeros. I have chosen this particular memory address because in my case, I have already shown in the last session that this comes under read write memory area. Okay. So now first let's execute this particular instruction, which will load a value 4 and all zeros to R1. Okay, so now what instruction we have is immediate post indexed. It's immediate because a constant value is taken here. So what should happen here is, whatever is the R7 content, that is this value, out of that bit shown here, should be loaded in the memory location pointed by R1. What's the memory location pointed by R1? It is 4 and all zeros as shown here. In this particular location, the content of ARM7. It means 6677 will be stored as 7766 here. That's the first thing that will happen. And ARM1 gets updated with ARM1 plus 4. What is ARM1? 4000 and all zeros. Okay, plus 4 means it will be 4, 1 2 3, 1 2 3 4. Okay, let's see that happening. So this got updated and 7766 appears here. Okay, the effective address will be ARM1 itself, but ARM1 is further modified based on whatever immediate constant is placed. We have to store 8 bits of data at the location ARM1. Now what is ARM1? ARM1 current value is 4 all zeros and 4. Let's see what it is. Okay, so in this particular location we want to store 8 bit of data which belongs to ARM7. What is ARM7? This from this 8 bits means 7 should be placed in this particular location. That is the first thing that should happen. After that we want to update ARM1, that is effective address is ARM1, which means ARM1 is nothing but in this particular location you have to load the value 77 because this has the value 77. Okay, then what should happen with ARM1? ARM1 initial value is that we have to add R3 LSL hash 1. Okay, LSL hash 1 means multiplied by 2. 2 should be added with 4. The final address will be 4 all zeros and 6. Let's see if that is what gets updated. Yeah, this got updated. ARM1 is 4 all zeros and 6. At the same time, if you notice this particular location 4 all zeros and 4, it got stored with 8 bits of data, that is 77. Next, what we are introducing is register post indexed. So what exactly do you mean by register post indexed as shown here? First of all, base register will be added with which content? It will be added with register content. So it is register. Okay, and what do you mean by post index? This addition happens after the memory access. So we want to load memory address content of ARM1. What is ARM1? ARM1 in our case is 4. Don't see this because I have not executed this command yet. Okay, to this I will be adding ARM3, that is 4. Okay, so this is the updated value of ARM1. At the same time, ARM0 will be updated with this particular location content. Let's see that happening. Okay, yes, so here ARM0 got the value 77 accessed from the memory location of ARM1 because that itself is effective address, which is 0x4 and all zeros. At the same time, ARM1 is updated with ARM1 plus R3 as expected here. Okay,